Now if we think of the algebraic definition of inverse, which is that um, the function and its inverse sort of undo each other, then think about what happens to the input here. First we multiply by 2 and then we subtract 1. So can I put a function together that does the exact opposite operations on the input in the exact opposite order? Okay. And I can do that pretty easily without doing that switch x and y and solve for y business. So I don't have to do that here. I can just quickly say, all right, instead of multiply by 2 and then subtract 1, I'm going to add 1 and then divide by 2. So there's the inverse of this particular function, which I can just throw together quickly. Others that you could do quickly, right? I could sort of quickly say, if f of x is x cubed, I know that the exact opposite operation of this is the cubed root of x. So I can just quickly say this is the inverse right here. Okay. So there's the basic process to find an inverse. You switch the roles of x and y and solve for y. Or sometimes you might be able to just look at the equation and reverse the operations and put the equation together that way. Okay. Do all functions have inverses? The answer to that is no, and I'll show you one example here that might look obvious. If I let f of x equal x squared, which is just our parabola, then we might quickly look at that and say, well, f inverse must then be the square root of x, because squaring something and square rooting something are inverse operations. The only problem with that is that it violates the graphic definition of inverse. So we run into a little problem here, which is this. X squared looks like this. Meanwhile, square root x looks like that. So there's a problem here because the dark curve and then, well, I guess they're both dark to you, but these two curves are not perfect mirror reflections across y equals x. Part of them is. These two pieces we don't have a problem with, but this part here we have a problem with. So we can't properly say that these two functions are inverses of each other. So how do we reconcile that? The truth is that x squared doesn't have an inverse. And here's why. X squared has no inverse because if we properly reflect this graph across y equals x, if we do that reflection strictly, we're going to end up with this curve right here. So the blue curve is x squared, and this is its reflection, which is not root x, but furthermore, it's not a function. Okay. So the only functions that have inverses are ones whose reflections are also functions. So there's a whole bunch of functions out there that don't have inverses. Other examples of functions that have no inverse. Okay, all of these functions that I'm writing here are not going to have any inverses. A graph that looks like this has no inverse. Why? Because I can see that if I reflect it, the reflection is not going to be a function. Okay, so essentially, just like we do a vertical line test to see if something is a function in the first place, we can do a horizontal line test to see if a function will have an inverse. Okay. Another function that has no inverse, f of x equals x squared plus 3. Okay, another parabola. It's not going to have an inverse because its reflection is not a function. Right? So there's lots of other functions out there besides parabolas, but that's the basic gist. I'll show you one more. Oops, I made that example C, but it's B. Another graph, just from looking at it. This function here is not going to have an inverse. Let's see. That curve there is part of the negative sine curve, irrelevant, but it's not going to have an inverse. And I can tell that because I just do a little horizontal line here, and this doesn't pass the horizontal line test, which means its reflection is not going to pass a vertical line test. Okay. So, kinds of exercises you're going to do, you'll be sketching inverses, finding inverses algebraically, if they have inverses at all. Okay. So, let's take an example like this. Find the inverse if it exists. All right, let's take this example here. F of x equals root x. Okay. Root x, if I just set about finding its inverse, I would do this. I would say x equals the square root of y. And now if I want to solve it for y, I will square both sides and get y equals x squared. So you might be thinking, well, we just established that x squared, this parabola, has no inverse. So why would we be saying the other way around that root x does have an inverse? But let's think about it. Square root of x looks like this. There's square root x. And that does have a proper reflection. That has a reflection that looks like this. So root x actually does have an inverse. And so just one important thing here, I won't say that x squared is the inverse of x. I'm actually going to use just part of that parabola. So the inverse of root x isn't x squared. I have to say it's just the right half of x squared. Just the right half of that parabola. And how do I say just the right half of the parabola? I'm going to specify that the domain is greater than or equal to 0. So it would be incorrect to state that these two functions are inverses of each other without specifying that we only mean the right half of the parabola. Okay? So while parabolas do not have inverse functions, half parabolas do have inverse functions. Okay? So there's a little bit of a nuance there that we're going to have to deal with, and we'll see more examples where that complication comes up. So take a look at the file that I'm going to send you. It has a few try these examples where you're going to be asked to sketch an inverse, possibly find an inverse algebraically, and decide whether or not a function has an inverse. All right. Have a great evening.